also had a good fortune experience last night. Absolute perfect storm of different factors coming together. As I was driving home, the hood came up and smashed into the windshield.
Oh no. Everybody okay?
Yeah, the windshield isn't, the hood isn't. But Grace did some deft hammer work and we managed to get it like bent back into where it would close again. And apparently we just like put a little bit of oil in and like that messed the headlights a little, and the latch, like the primary latch was like bent outward. And the secondary latch was also like bent outward. So it was like I noticed it like popping up and we stopped and like checked it out and looked at it and was like, okay, we'll just close it really good and that'll be fine. And, a minute later,
yeah, no good.
That was really scary.
I'm scared. Was anyone else on the road with you?
I mean, Grace was in the car with me, but no other vehicles were.
That's lucky.
Yeah.
All things considered, as long as the hood can be closed, it's functional. So your windshield might not be that bad to pay for that. So my 2001 Subaru, my worst maintenance accident that I had with it was morning, Miranda.
Morning.
When I was in grad school, I'm very, very poor. I had a leak in one of the tires, and so rather than pay AAA to come tow it the 2 blocks in Boulder to the tire shop, I just took off the tire, took it to the tire shop, got it patched, brought it back, put it back on myself. Nobody tells you though that even if you crank on them really hard, if you put a tire on yourself, you have to check the lug nuts again after 100 miles, because if you didn't seat it properly, they can wiggle loose.
Oh, yeah.
I figured that out when I was driving through the Black Hills in South Dakota with no cell phone reception when my rear wheel fell off. And wound up like 200 yards away in somebody's front yard. And that was a lot more expensive than a windshield and a hood, because I had to replace like the entire rear end of the car, the suspension and axle. And, so it's doing your own maintenance on your cars can be touchy sometimes. Not that you did that on yours, but like it's good enough. And then it's not. All right. Couple of good relevant quiz questions. So for the methoxy group, in terms of activators, deactivators, we consider it moderate activator, like the OR. So OR is just any ether group attached to a benzene ring. So yes, it'd be on a moderate activator. And so, and just like you guessed, whatever's the most, so remember the way that these activators and deactivators work is deactivators raise the transition state barriers and activators lower transition state barriers. So the stronger activator is always going to be in control, because lowering the activation energy is what's going to drive the reaction forward, versus a deactivator might raise activation energies, but that's not going to control what product you get if you have an activator present as well, because lowering the activation rate or activation energy is going to be more critical there. And if you have 2 strong activators that are opposing each other, that aren't working together, you would want to, and you could either find a different table that has the label more in order, but in general, it's going to be pretty clear. They're either going to be working together, and I believe that with the OH and the methoxy group, they actually work together, because you can satisfy both of them by putting, so they're not really in opposition to each other, because the alcohol group and the methoxy group being meta relative to each other means that there's 3 positions, or Yeah, there are three positions that are ortho or para to both of these functional groups. So you can satisfy all of them. Which leads me to the next question, which was with this group, so those three positions all satisfy both of those activators. Are these two functional groups big enough for sterics to really prohibit that ortho to both? Those are not that large of a group. It might make this middle position a little bit less likely than it would otherwise be, but probably not significantly. So I mean, maybe 10% difference. We're still going to see some of it. If it was a T-butoxy group, or if it was two ethers instead of an ether and an alcohol, you know, the larger you make those things, the more you'll see that. But it is more of a sliding scale rather than a binary yes no. Until you get to the really big things. And as far as whether you'd expect the, you know, and so really it can't really pick either of those. There's one carbon for both of them. They're both ortho to one strong activator and para to another activator. So you're going to get probably roughly equal amounts of the two of these two, with slightly less of the one that's got the sterics involved. And just to clarify also, question about, is it really sterics if it's lone pairs that are taking up the space? It is still sterics, because remember, everything that's really taking up space is all electrons. So even if it's not lone pairs, it's still, anytime we're talking about electron-electron repulsion, that is sterics. Just because I can't resist, because I love this visual. Remember, the nucleus is the size of a baseball at Oracle Park, at the pitcher's mound, and the rest of the stadium is the electron column, right? So hugely, the volume favors the electrons. So it's always really just electrons pushing on other electrons. In fact, when you touch something and you feel it pushing back against you, you're not actually touching nuclei. That's just the electron-electron repulsion from the electrons on the surface pushing it against the electrons in your finger. Unless you start getting into something like X-ray diffraction, you're never actually going to have direct contact between nuclei. And actually more like alpha, after you did a Rutherford gold foil experiment, you can get close to it. The problem is if you actually have nuclei touching other nuclei, they never actually touch each other because they're positively charged, right? So the closer they get, the further they push each other, or the harder they push each other apart. If you actually force them together enough that they actually touch, what you really get is a fusion reaction. And now we're in a whole different ballpark of questions. Make sure I addressed all of this. This was last year. I don't think it's that relevant, so I'm not sure why I left that in there, other than I forgot to delete it. So here's a recap. If a benzene ring has more than one substituent, the directors will either work with each other, like in the case of the nitration of dinitrotoluene. If we do this, the nitro groups are meta directors, and the methyl group is an OP director. So the only position that satisfies all of them is ortho to the methyl group and meta to both of the nitro groups. So always just double check that there's not an option that satisfies everything. Or if they do oppose each other, then you go with the most powerful activator is in control as the director. So if we were looking at these two, the methyl group is weakly activating, the OH is moderately active, strongly activating, strongly activating. So that means the OH group gets to determine where the next substitution occurs. So we wind up putting it in the ortho position, the OH, and this would be a nitration reaction. So our final product here. Look like that. Do we need to draw the other ortho product? Same thing, right? Nice thing about these planar molecules. And up at the top, you would wind up with trinitrotoluene. So we put the nitro where on that carbon that I have marked there. All right, so we can do a little bit more practice here. See if you can do this without consulting at least for the ones that are only singly substituted. So you can remember what's my OP directory, what's a meta director. And remember, acetyl chloride is that molecule. So remember with the Friedel-Crafts acylation, wind up putting the carbonyl goes adjacent to the benzene ring. So you effectively wind up with it being conjugated with the benzene ring. And so it's the same thing. It's just the only thing that can really change this is if we have something other than a methyl. If it's not acetyl chloride, if it's isopropyl chloride or something like that. It wouldn't be isopropyl chloride, there'd be isopropyl chloride. You can't have isopropyl chloride. It would be isobutyl. But that's the N propanoyl chloride. So because this is effectively a acid group, it's an acid derivative. So it has to be at the end of a carbon chain.
So you're trying to make the CH different.
Right. Yeah, you can do that. You can have, you could have isobutyl chloride or something like that.
I think it's
Yeah, no, that would be the not we wouldn't call it dimethyl. It would be methyl propanoyl chloride.
Yeah.
I was trying to use the common name, and then I realized, why would I do that? That's a silly thing to do. All right. So then for the for the bromine's weakly deactivating, but that doesn't have that lone pair, so it's still an OP director. So for the second one, we would wind up with two possibilities. That molecule or that molecule. The acetyl group either in the ortho position next to the bromine or the para position opposite the bromine. Right, so easy enough when it's just one thing that's all substituted, even if you do have to consult your table for briefly. If you have two things present, see if you need to worry about which one's stronger, because if they're going to work together, it's not so bad. So the NO2 is a meta director and it's next to an orthoperic director. So these two positions satisfy both of them. So you get some of that product and some of the para product. And the last one is exactly the same one that we did on the quiz, right? Just on the quiz we did, it was a chlorination, and here it's an acetylation. So in this case, we would put it those three positions. So we actually would get three distinct products in this case. And once again, they're working together in that case. So was that actually the one, or did I give you something? Those are the, these ones were, except just with the chloride instead of acetyl chloride. Oh, okay, I thought it was just chlorine. These ones were also on the quiz. Anybody have any questions about these? We don't have any substitutions. It's really pretty straightforward as soon as you can recognize the reactions, right? Fuming sulfuric acid means you're adding in a sulfonic acid group, so SO3H group. Bromine with iron means you're adding bromine. Here's more practice. And again, see if you can do these without consulting your table as much as possible, because once you start seeing the patterns, it does go pretty quickly. So for this first one, we're going to add a chlorine, right? Where do we put the chlorine? Para to the bromine is also meta to the two other groups, which are meta directors. So everything can be satisfied. And this brings up another good point. Where do we draw the line between saying no reaction will happen? If we've got a strongly deactivated benzene ring, at what point do we say no reaction? Essentially, if we have, so I believe bromine is weakly deactivating, plus the two esters are going to be moderately deactivating. You have two moderately deactivating and a weakly deactivating. This effectively, we're going to see no reaction. Really, it'll happen just so slowly that we would really want to do something to push it along. We'd have to find some way to tweak the process. Like maybe since the chlorine is weakly activating or weakly deactivating, maybe we would change the order of the substitutions and add the two ester groups after we add the chlorine. Might actually be a more effective way to do this. If you have two strongly deactivating groups and no activating groups, we can effectively say that the reaction won't happen. And so I'm not going to be all that picky about there. That is a fine line because it's kind of semantics. We know by this point that when we say no reaction, what we're really saying is it doesn't happen at a measurable rate. So I'm not going to be that picky. If you recognize that and say no reaction, that would still be full credit. So if you have three deactivating groups, or two strongly deactivating groups. I guess we can call that. So, three deactivating groups of any strength or two strongly deactivating. Of course, none of that applies if we have an activating group, because remember, activating groups work in the opposite way. Activating groups work by lowering activation energies for the different positions, and so activating groups are more important than deactivating groups. So this rule goes out the window the second we're dealing with activating groups. Which is one of the reasons why you can have, why this reaction can happen, why you can nitrate dinitrotoluene, is because yes, it's got two strongly deactivating groups on it, but it also has an activating group. The activating group is more important. It's a reason that we don't have trinitrobenzene. We have trinitrotoluene instead, is because you need that activating group for the process to happen. So in the case of B, we have two methyl groups that are both ortho-para-directors. And we have, and remember the methyl groups are weakly activating. And we have the methoxy group. Lone pairs make the methoxy group more strongly activating. I think it's listed as moderately activating, but it's more strongly activating than the methyl groups. So that puts the OCH in the driver's seat. So we want ortho or para to the methoxy group. So we wind up with the two products. Put a nitro group there. The other product would be if we put a nitro group here. And so this is one of these mechanisms, one of these processes. It's one of our fundamental mechanisms. It gets used all the time, gets asked about all the time on standardized tests. And it's really, there's like two more mechanisms in this chapter after this. And so it's really the bulk of the aromatic reactions that you're going to see are going to be these ones. So we're taking our time, even though it's getting a little repetitive. Just to make sure that this is really kind of second nature, because in identifying electron donating, electron withdrawing continues to show up as well. So it's really something we want to have backwards and forwards, so to speak. If we're looking at, so fuming sulfuric acid, we've got a T-butyl group, we've got a methyl group, they're both weakly activating. So, and they're roughly the same strength as far as how activating they are. So we aren't going to let the activator strength determine which product we make. In this case, we'll go with sterics. They're both the same level of activating, but the T-butyl group is bigger, which means it's harder to put our sulfonate group ortho position relative to the T-butyl group. So the more common product would be this one, where the SO3H group is adjacent to the methyl. If we were splitting hairs, the T-butyl group is just barely more activating, but it's not enough to overcome the sterics there. It's the bigger deal in this case is the sterics. Now, if it was a T-butoxy group, then all of a sudden we're in a whole different category of activating, right? And then that takes over despite the sterics. I thought this wasn't supposed to hit until tomorrow or Thursday. It's not expecting snow today.
It's really wet. It's like slushy.
Yeah. I saw now that that Thursday, we're now expecting 6 inches of snow at my house. And 2 inches overnight on Wednesday night. So that's the thing that's happening.
I always have to load music gear and stuff.
Not
Hard openings and,
after this term.
yeah, this is going after this.
This Thursday, right? Did you find out about Davis?
The Thursday or Friday.
Yes.
Excuse me. All right, is there anything tricky about this last one? It's 3-way substituted. Got 3 different categories, levels of activator and deactivator, right? So when in doubt, find the most strongly activating group, put it in the driver's seat. OH is the most strongly activating out of this group. So we're going to put our new nitro group has to be ortho or para to the OH. There's only one position left, right? That is ortho or para. The activator. All right, so how are we feeling about these? Might not have that table memorized yet, but at the very least have a pretty good handle on it. For pi bonds versus lone pairs, most important distinction. Cool. This is just more practice. We'll skip this for now. So let's talk about a slightly different mechanism. If we have a substitution happening on a benzene ring and we're not replacing a hydrogen, then we can actually get the reaction to go through a nucleophilic substitution. It's not all that common because you're dealing with a electron-rich area. So getting a nucleophilic substitution to happen is not easy. Generally, this only happens if you can meet all 3 of these criteria. So you have to have a strongly deactivating group, a powerful electron withdrawing group, which is usually nitrate, a nitro group. You have to have a really good leaving group, generally a halide. And you have to have your leaving group either ortho or para to the electron withdrawing group. If all 3 of those are not met, then the reaction doesn't happen. So the leaving group being ortho or para relative to the electron withdrawing group, does that suggest anything about the mechanism, about what's happening here? How come deactivating groups were meta-directors directors and orthoperic directors were activating groups. What was it that made those two things true?
Where the carbon.
Right, it had to do with where the intermediate put the carbocation, right? So at least in the most broad sense, it's resonance. Again, resonance and electronegativity and sterics, those are your three. It's always one of those three. In this case, the fact that it's ortho or para tells us it's going to be resonance to some respect, right? Because that's why it alternated, things alternated positions was the carbocation resonated from one position and then skipped to carbon and resonated to the next position when we had that sigma complex. So even just really broadly, that tells us that we're going to have something happening where we have a where resonance is going to play a role. And so it's similar actually to the mechanism of electrophilic substitution. The difference here is really just that we wind up with the nucleophile attacking where something other than a hydrogen is attached. You wind up making a complex with a bunch of resonance structures that's just like the sigma complex. Except now we have an extra electron. Instead of being electron deficient for an electrophilic substitution, it's a nucleophilic substitution, we have extra electrons. Because our nucleophile brought a pair of electrons instead of breaking a pi bond to take a pair of electrons. So this complex, which is called the Meisenheimer complex, is effectively a sigma complex with a negative charge instead of a positive charge. So it makes sense that the resonance would be backwards. Nitro groups, when it was a positive charge, you wanted the carbocation to not be directly adjacent to the nitro group, right? Because it's electron withdrawing. So on the flip side, if it's electron withdrawing, putting a negative charge adjacent to the nitro group should be more stabilizing. And so, and again, this should look really familiar. If anything, it's going to be hard to tell these apart because they're too similar. So just remember, if it's a nucleophilic substitution, it means you're going to have extra electrons. So you get a negative charge. Right? And the general gist of what we're going to see is break the aromaticity by adding an extra pair of electrons, which can resonate around in the Meisenheimer complex. And then when your leaving group leaves, you can reform your benzene ring. When you reform your benzene ring, you get your final product. So again, this only happens if all three of these criteria are met. You need your powerful electron withdrawing group because you need that extra resonance and that electron withdrawing capability to stabilize having the extra electrons there. You need a good leaving group because, well, we need something to leave and reform the benzene at some point. And your leaving group must be ortho or para to the electron withdrawing group so that that Meisenheimer complex can put the negative charge next to the nitro group. And really, it's number two is not about kinetics. These first two are more about kinetics. You need to lower activation energies to get them happen. Sorry, the first two. 1 and 3 are about the kinetics. 2 is less about the kinetics and more the thermodynamics. You need to be making something that is more stable than what you started with so that you have a driving force downhill in energy to cause this reaction to happen. If you try to get this reaction to happen backwards, it won't happen, even though the kinetics aren't all that different. Going backwards for this reaction isn't that hard to get to the Meisenheimer complex, but you don't have, if you're not making something that's more stable than what you started with, there's no driving force for the leaving group to leave. So it's, even though there's a force to reform the aromaticity, it's going to be whichever one is more favorable to be on its own is the one that's going to be the leading group. So this one doesn't really happen backwards, at least not without a whole bunch of Le Chatelier's principle and tweaking the mechanism a little bit. All right, so let's try an example. So predict the product of the following reaction. Got a good nucleophile, got a strong electron withdrawing group. We've got two choices of leaving group. So which one do we replace with the methoxy? And why? Because it's the para position. Bromine being meta to the nitro group means that the bromine can't be the target of this nucleophilic substitution, because that Eisenheimer complex is just not going to put the negative charge on the nitro group if we do that. So our final product then bromine gets left alone. Change the chlorine to a methoxy group. So while this is one more thing to have to memorize, at the same time, it's really easy to recognize when this is happening, because this is not one of our 5 electrophilic substitutions, and it has to meet very specific criteria. So a nitro group with an electrophile and a good leaving group should already sort of put you in this sort of mindset, which again still requires a little bit of memorizing to become fluent with it, but it's not too bad. And I think we'll probably do something similar for midterm in this class that we did last quarter with half page of notes. I think that was an adequate amount of notes without being too much space. Half page is small enough that you can find everything that you have written, versus if I gave you 3 pages, then you lose yourself in your notes. And this one doesn't make a whole lot of sense yet. Because we need to learn. What's that? What are your thoughts? Maybe we've gone over them and I've forgotten. I get the order mixed up sometimes.
So if you have bromine on there, start with bromine, then nitrogen.
Good.
And then do solid instead of hydroxy. So hydroxy group paired with nitrogen, and then reduce the.
That's the one we haven't covered yet. So you have almost all the steps. So if you start with benzene, you can brominate benzene with Br2 and Fe to make bromobenzene. And then we can nitrate that, and bromobenzene being an orthopara director means that when we brominate or when we nitrate this, we're stuck in putting it in one of 3 spots. And the fact that bromine is such a large nucleophile, or such a large substituent, means we're going to favor putting it in the para position. It's not going to be a great yield because it's still, driven by statistics and sterics. But our major product in that case would be nitrobromobenzene. And then we can do the nucleophilic substitution we just saw, because we've got a strongly electron withdrawing group para to the bromine. So we would just use, so this one would be the nitric acid and sulfuric acid. And then if you use hydroxide as your nucleophile and heat, you wind up with the para-nitrophenol. So that got us almost all the way to our target molecule. One thing that we're missing, we haven't talked about yet, is the fact that we can reduce nitro groups. Nitro groups can be turned into amines by exposure to a strong reducing agent. Which did we go over that in a different chapter or something? I just don't have it listed here. Yeah, the next step is going to be, if we look at the reaction summary for this chapter, it's not on my slides here yet, but the last step would be, we just need to reduce that nitro group, and there are a couple reagents that do that. We just need a strong reducing agent. I believe sodium borohydride works.
There's always the big guns.
Yeah, there's always lithium aluminum hydride, right? Open it. There. So that would be overkill to use a hydride source in this case. All you really need is an easily oxidized metal like iron or zinc and some HCl. And then you protonate it. Or sorry, and then you sodium hydroxide. Going to go through a different mechanism. But effectively, we can take, it's just a reduction reaction that allows us to take an NO2 group to an NH2 group. And so we hadn't specifically gone over that one yet, which is why it's not immediately obvious. We've done everything except that last one. So just either just iron or zinc in HCl. Follow it up. Probably this hydroxide is just there to neutralize the excess HCl. maybe, right, and the fact that the amine is a weak base. The phenol can be deprotonated. The nitrogen probably is easier to protonate than the phenol. The amine is easier to protonate than the phenol because if you protonate the amine group, then you wind up with that lone pair no longer being able to act as a resonance structure. So you actually lose the resonance structure when you protonate the nitrogen there. So it should be easier to deprotonate than the phenol. So that could be what's going on there. A lot of times though, with our reactions, we don't necessarily distinguish if it's something that's easily protonated or deprotonated. We don't necessarily distinguish between them. If it's something that's really unstable, unless it's protonated, then we make sure we have that extra protonation step. But regardless, I don't think that's a mechanism we're going into in detail because it's a reduction reaction with metals involved, which means there's some weirdness happening with metal oxidation states. So we won't spend too much time on that. All right. So there's one other substitution mechanism that we can have and on benzenes. And it's a weird one. It's actually called elimination addition. So as you might guess, it goes through two successive steps. It's not a straight up elimination, or sorry, a straight up substitution. What happens first is an elimination reaction, and then you follow that with an addition. And it takes a lot to get this to happen. Basically, you have to get up to 350 Celsius in a very basic solution with a strong nucleophile for this to happen. But it doesn't go through orthopara substitution. So it's not orthopara and you don't get meta substitution. So that tells us that the resonance is not really playing much of a role here. In fact, if you do this with a chlorine that is para relative to toluene, you get a mixture of the para and the meta product, which is this is the only time we see para and meta showing up in the same reaction. Which again is a clue that there's something really weird going on. And so what they did is they actually did this with isotopic labeling, where they said, okay, we're going to take benzene and we're going to put a carbon 13 where the chlorine is attached. And then they put it through this mechanism. And what they saw is that the chlorine, when they replaced the chlorine with a nitrogen, they got a mixture of nitrogen attached to the same carbon where the chlorine was and nitrogen attached adjacent to where the chlorine was. So that right there tells us it can't just be a straight up substitution, right? Because substitutions by definition only substitute where your leaving group was attached. And so the best understanding at this point of how this happens, it's pretty well supported, even if it is weird and counterintuitive, is that you make an intermediate called benzene. So as you might expect, benzene is benzene, but with a triple bond. And as you might expect, it's very unstable because even though all of the carbons in benzene are satisfied as far as the valences go, that triple bond should be linear based on Vesper geometries, right? And we're forcing it to be, those angles to be 120 degrees instead of 180. So it's bent very, very far out of the ideal geometry. And so that makes it an easy attack for something else. So what happens with this mechanism is if you've got a good leaving group and you put it in very basic conditions, you wind up with your nucleophile first acting as a base and just deprotonating, and you go through an E2 reaction. Actually, sorry, E1 reaction. So you pull a hydrogen off, you deprotonate adjacent to the halide, and now we've got an extra pair of electrons right there. So that extra pair of electrons can move over and make a triple bond when your leaving group leaves. So once again, we need a good leaving group for this to happen. So we need a strong base, good leaving group, and we can see, and very basic conditions. We start to see this happening. Then you make this benzyne intermediate. And then you just treat the second pi bond just like any other alkene, essentially. It can go through an addition reaction. You just need a nucleophile around. Where it's a little bit different is that it doesn't start by protonating the pi bonds. In most of our addition reactions, we started with the proton transfer to make it a carbocation, which would then be a good target for the nucleophile. Because we're in such basic conditions, we don't have that happening here. Instead, you need a strong enough nucleophile that it will attack one of those carbons, despite the fact that there's a whole bunch of pi electrons around. So this is not a super efficient reaction as far as yield and rates go. But it is a mechanism that can happen that is distinct from our other aromatic substitutions. So electrophilic aromatic substitution is where we spent most of our time so far. It's the most common of these. If you're replacing a leaving group instead of replacing a hydrogen, then it's got to be either the nucleophilic aromatic substitution or this elimination addition. And one of the reasons that they know that this is the real mechanism is somebody figured out, like, well, if benzyne is real, then it should be able to act as a dienophile because it's a highly strained, unstable pi bond that should want to react with a diene, a conjugated diene, in a Diels-Alder reaction. And they were able to do that. If you put benzene and furan together under basic conditions, you can actually wind up with the benzyne interacting and making a Diels-Alder product. So this is effectively one way that they were able to prove that this happens, because the Diels-Alder mechanism is a pretty well understood mechanism. And so they basically, well, we can, if our benzyne reaction is accurate, that intermediate should be able to go through this other process. And so they tested it, and then they were able to detect a measurable amount of that cycloadduct. So, and it's one of those light bulb moments that happens years later than it should. I just realized where the word adduct comes from. It's a portmanteau of addition product. An adduct is the addition product. So a cycloadduct is the cycloaddition product. Chemists, man. When in doubt, just slam some words together and make it a new word. All right. So let's take our break. Let's come back at 5 after. This is, I believe, is the last mechanism in this chapter. Then we'll start getting into carbonyl chemistry. And leave aromatics and resonance alone for a little bit. That's a lie. We'll leave aromatics alone for a little bit.
If there's like a long tradition, relatively long tradition of chemistry literature.
Yeah,
Slam words together.
it is. That's how they get some of those wonderful words that don't translate English, like Schadenfreude or however you pronounce it. Joy in the pain of another, or whatever it is.
Shape of fruit.
Have
Shame,
you ever
yeah.
listened or seen Avenue Q, the musical with
Oh,
the
yeah.
puppets? They have a song called Schadenfreude. It's really, it's funny. Gary Coleman sings it.
Nice.
Yeah, getting joy from other people's pain. I think it's very fucked up if you think about it.
My favorite German word is for suffering.
What is it?
Unterwasser.
Unterseeboot.
This is where U-boat comes from.
Oh, really?
So actually, here's a good music recommendation for you as well. But the word for airplane in Thai is krongvin, which translates to flying engine. And they're also a really good sort of almost ambient, mostly instrumental jam band, just a bass, a guitar, and a drum kit.
Okay.
But they do a lot of like Southeast Asian mixed with Spanish style guitar. It's a lot of fun. They have a really good YouTube or a really good concert on YouTube. It's spelled because it's a Thai word. I don't like instrumental music. There's no markers in here. I don't like instrumental music all that much, but their songwriting is still good. It's just not something you can say for a lot of instrumentals.
Yeah, I personally prefer instrumental music.
It's
As long
really
as it's
yeah, it's well written, and the spelling might not be right, but that's close enough that you'll be able to get there.
American musical trio.
Yeah, they do a lot of stuff with Leon Bridges. The stuff that they do that's not instrumental, they have Leon Bridges, who's a soul singer from Austin, who does really good stuff too. I did get it on my second try. And you know that they can't be that bad. This is the one that I was thinking of. They've got a whole concert on there. I throw this same concert on all the time when I'm just like doing housework with the kids, because it's the kids. It doesn't get them wound up. It's pretty mellow.
What's this? I didn't even put this here.
I did. I grabbed that like, oh, I've been seeing these around campus. That's probably. I think I grabbed it from the math lounge upstairs on my way by.
Yeah, I was about to give these guys one, so I've got a bunch of.
Yeah, I was just double checking that it is in fact at on campus. That it wasn't something I figured, but
Yeah, right over here, and then right over there.
yeah.
Yeah, if there's like a bunch of snow, it's gonna be really hard. There's no like all indoor.
The some of the wood over there from the breezeway side, so maybe they're trying to have that.
That would be super cool. We could just like get people to go through
Yeah,
instead of
from the
outdoors.
breezeway side, it was open going this way, so I don't know.
Yeah, I don't know that they're opening it up to go through. I know that they let the student accessibility services over there.
Oh, that's probably what it is.
I think it's just like that.
time thing you were talking about. Watching the snow. I know it is. Sean, for the lab assignment, do you want us to do all 16 of the questions from the Canvas document? Or
No, just the ones that I put. I'll adjust the Canvas document.
Okay. Yeah, I left my my sheet in the lab, so I pulled up the Canvas one. It's like, this looks like a lot more than I remember.
Yeah, I'll after class today, I'll go do that. I'm gonna run over, grab my coffee mug so I can have some coffee. But yeah, I think there's like 5 questions. I'll put that version up as soon as I get a chance.
Cool, thank you.
After lab today,
I don't know. It depends on, I'm going to get my oil changed between class and lab. And depending on how long that takes, I have to work on the lab. Wait, for what? To work on the lab?
so from last Tuesday,
Mhm.
I was wondering if you would be able to work on last Tuesday's lab after lab today.
Possibly, yes, yeah. I have to get my oil changed and then run something to work, but hopefully if the oil change only takes 20 minutes, then yes.
Classic. Oh, they're wrong out
Sean kind of beat you to it, but
I was looking at that on the table over there.
Wow.
cool stuff.
Oh my gosh.
Grace's art opening is happening through the Duke Theater, and my band is playing there.
Awesome. That's Thursday?
Yeah.
Ooh, are you guys gonna start playing at 5 or where do you guys play?
So the way that I'm sort of organizing the event is it's going to start over here at the Holding Gallery, where they're doing the closing ceremony for the staff and faculty show. They're going to do artist talks. There's 5 or 6 people, so they're probably going to go on a bit, and they're starting at 5:30. And then once that's done, somewhere in the area of 6, maybe 6:15-ish, then we're gonna start playing music over there at the Duke Theater, and one of us, the flute player, is going to do the Pied Piper thing. It's start playing flute and get the follower over there.
Oh, cool.
Where's the foyer gallery?
It's just the front of the theater.
Oh, okay.
Oh my gosh, that's awesome.
not only is there super cool music going on, also, I mean, the ceramic art that's going on is all like locally sourced clay and glazed materials. Me and Grace have been hiking and collecting for the last like 2 years or so. And she's been melting them down to kill them, sinking them. Now she's presenting artworks that she's made from all that.
Yeah, sounds like the big payoff at the end of a long project.
Looking for that, yeah. It's been kind of like a thing where, because of this sort of artificial deadline, because Brian wanted Grace to do that, like, on the same day as the staff faculty show closing, so that there'd be more people at her event. So she's like just busting ass, and she's been like really sacrificing hours and hours of sleep in order to get it all together, like time. But it's like it's a really big project. There's like a big map of Alpine County that's going up, which is going to be correlated with photographs of locations where materials are planted, as well as like with samples of those materials, raw and fired, and like all this stuff going on. And then there's like the artworks themselves, and she's like working on that. She's pretty much kind of, you know, Excel already, but at this point, like, there's this one piece. The image on this is it's still in pieces. It's a self-portrait that she made, fired, and it's smashed, and glazed with a bunch of different glaze materials.
Well, it sounds like you can get like a really cool page.
It is sort of brilliant, and right now she's in the process of gluing those pieces back together.
Wow.
That's very cool. It's like a puzzle where the pieces are all irregularly shaped. They're not color coded, they're the opposite of color coded. They're all different glazes going to different pieces. So it's a pretty hard time right now, presently, over the ceramics lab. Together, finding what goes together.
Sounds like she's super passionate about it. I hope she's not losing too much.
It's one of those things where she's probably started seeing it in her dreams. So I've told you what my PI used to say about that. You're not dreaming about chemistry, you're not working hard enough.
What did you go outside for?
Give
You're
her a
outside?
compliment.
Uh,
I should have a quick shower. All right. So quick recap. We've got our electrophilic aromatic substitution, which is pretty easy to recognize. There's only 5 mechanisms. That's one of the orthopara directors. If we have a nucleophile instead of an electrophile, then we have 2 choices. It'll either go through this nucleophilic aromatic substitution, and that's when we have to have all 3 criteria met. Powerful electron withdrawing group, good leaving group, and your leaving group must be orthopara to the electron withdrawing group. If you have a nucleophile in a good leaving group, but you don't have the electron withdrawing group, and if it reacts at all, it's going to go through this benzyne reaction. So where we see the difference is that with the nucleophilic substitution, we always put our new nucleophile in the same spot as our leaving group. But with the benzyne substitution, the elimination addition, we wind up with 2 possible products every time. It will always make 2 possible products because there are 2 sides to that benzyne intermediate that are, for all intents and purposes, identical as far as being a target for a nucleophile. I guess the one time you don't get two distinct products is if you started from just benzene, because all of your carbons are equivalent in that case. All right, so draw both products that are obtained when 4-chloro-2-methyl-toluene is treated with sodium amide followed by treatment with H3O+. So sodium amide followed by H3O+, strong base. Start by drawing our reactant and see what we would get. So here's our reactant, 4-chloro-2-methyl-toluene. So toluene is methylbenzene, right? And so the numbers are going to be referring to that first methyl group on methylbenzene. So 4-chloro, 1, 2, 3, 4. So 4-chloro means the chloro is in a para position. And 2-methyl means you've got a methyl adjacent to the first methyl. So when we go through this intermediate, again, it can be helpful to draw the intermediate. And sometimes, especially in these substitute cases, there's more than one possible intermediate. So that means there's two places we can add our nucleophile, and our nucleophile is NH2. The negative charge is the sodium amide. And really, so it looks like there's three places, but because we have two identical substituents, two methyls, we can't tell apart from each other. Realistically speaking, it can be ortho to one methyl, para to the other, para to the one methyl, ortho to the other. Or it could be on this carbon, where it's going to be ortho to one methyl and meta to the other. I said ortho and para, I meant para and meta for the first one. So we wind up with our final products of we can put our NH2 here. We can put our NH2 here, but that's the same molecule. Or we could put our NH2 There. See, for the first two, we wind up with these two are para relative to each other, and these two are meta. And for this one, these two are para. These two are meta. So it's because the two methyl groups are identical, that's the same product. And again, if you're ever unsure, try naming them. If you come up with the same name for both of them, it's probably the same molecule. So if we named this as an aniline, as dimethyl aniline, or you could name it as methyl amino toluene, either way. But regardless, for this, for both of these first two, it's going to be, if it's the aniline, it's going to be 3,4-dimethyl aniline. Either way, it just matters which way you count it. It's either 1, 2, 3, 4, or 1, 2, 3, 4. So same molecule. Versus down here, this would be 2, 3-dimethyl aniline, as opposed to 3, 4-dimethyl aniline. So that's probably the trickiest thing about the elimination addition reaction, is determining what are your 1 or 2 benzyne intermediates, and does that give you more than one possible product? And it could give you up to 3 possible products. It will never give you more than 3 possible products, because at the very beginning, those are the only 3 carbons that can be part of the benzyne reaction, right? Because it has to be the carbon that your leaving group's attached to, and one of the 2 carbons on either side of it. And there's no rearrangement or anything, right? So at most, you could have 3 products. More common that you just have 1 product. Let's do a synthesis one. Starting from benzene and using any of the reactions that we've seen in this chapter, how could we make anisole, which is methoxybenzene? It only takes 2 steps. Just like with a lot of our reactions, you just need to put a good leaving group on, and that opens a lot of possibilities, right? In this case, because we're trying to put on a molecule or a substituent that is a good nucleophile and a strong base, this is pretty straightforward. If we want to do something that wasn't a good nucleophile, then that's a trickier problem, perhaps. Thing is, if it's not a strong nucleophile, it might be a good electrophile, or at least there might be a way to make it go through an electrophilic reaction too. So there are sort of two diverging pathways here when it comes to synthesis, depending on what you're trying to attach. All right, so it's worth going through. Quick recap of the mechanisms, because we do have 3 different mechanisms, and they all accomplish similar things, so it's easy to get them mixed up. They all make up a substitution. It's just a matter, is it electrophilic or nucleophilic? Both the elimination addition and the nucleophilic aromatic substitution are both attaching a nucleophile. It's just a matter of, does it do it directly and make this Meisenheimer complex, or does it go through that benzyne intermediate? But all of these are, you can kind of tell how significant these reactions are by the fact that they each have an intermediate with its own name. Generally, we would just call an intermediate, well, it's an intermediate. The fact that all 3 of these have a specific name tells you that they're pretty well studied and fairly common reactions. Anything jump out? Anybody have any questions for clarification about the differences between these? If I'm being thorough and doing my job, you shouldn't have too much, but it's always hard to remember to talk about all the details. So if we want to decide which of these mechanisms we're going to go through, here's a flowchart view of it. Are we talking electrophilic or nucleophilic? It's electrophilic, then it's pretty straightforward. We only have 5 of them really. Bromination, chlorination, base 6. Bromination, chlorination, sulfonation, nitration, acylation, alkylation. But they all were pretty recognizable. They all had Lewis acids present for the most part, right? And so that made it pretty obvious that we were making an electrophile. And we're pretty good at recognizing nucleophiles at this point. We've spent a lot of time identifying nucleophiles. So basically, if you can't look at it and see a nucleophile, it's probably electrophilic. And if it's nucleophilic, this is the one that was really, really constrained. It had to have all 3 criteria met. And if not, it'll either not react or you get the elimination addition. And the elimination addition just means you have to, it's got to be really basic conditions in the high temperatures. Right, so it can be a little tricky to tell them apart, but at the same time, they all are fairly specific. And once you know what to look for, they're pretty easy to recognize. Is there a bird? Does anybody else hear that?
Yeah, it sounds.
Okay. I wasn't sure if there was like something unmuted on the computer or.
Little group of birds, basically.
I noticed like 6 robins in my backyard yesterday, and they don't like the snow very much. So yeah, those migratory birds are pretty good.
Around.
Yeah.
It was like staying under the ring.
But better keep my cat inside. She loves songbirds. She thinks she can take a Stellar's jay, but she's only about the same size as a Stellar's jay, so. But she has brought back robins, and woodpeckers before. All right, so let's practice determining the mechanism. If you know what the product is, it's really straightforward. Because the other thing that's really obvious if you know the product is that the electrophilic substitution is always replacing a hydrogen. The other two substitutions are replacing a halogen or some good leaving group, which is most commonly a halogen. Right, so with that in mind, there's our electrophilic. We've got our Lewis acid. We're replacing a hydrogen. Meets all our criteria there. Substitution, but without a nitro group attached, without an electron withdrawing group attached, that's going to be our benzyne. Mechanism or elimination addition. And down here, you've got our strong electron withdrawing group, good leaving group, ortho or para to the leaving group. So that's going to give us our substitution nucleophilic aromatic. So it's not SN1 or SN2, it's SNAR. So I don't know why they go through the trouble of defining SN1, SN2, SNAR, and then don't give electrophilic mechanisms the same treatment, but nobody ever writes SEAR or electrophilic aromatic substitution. Seems like that we already have the mechanisms or the terminology in place, but nobody ever writes that. They just call it electrophilic substitution. Just maybe because then it would get confused with elimination reactions. Let's see whether any other let's look at the reaction summary. Make sure we've covered all of the ancillary reactions. So just a quick recap on oxidation reactions. Remember, we did have that benzylic oxidation from last chapter. If you have a benzylic carbon that has a hydrogen on it, and you expose it to a chromate or a permanganate, you can oxidize it to form the carboxylic acid. So that is one option where if you add a methyl group, you can then turn around and turn it into a benzoic acid. You can also reduce, we also know about reducing nitro groups with iron or zinc in these conditions. You can, if you use a zinc mercury alloy, you can, notice that it doesn't say or zinc. It's saying or mercury, it's zinc parentheses mercury, which means there's something weird going on with the mechanism. Usually that means if it's two metals, that means it's an alloy. But it can mean zinc metal in the presence of a mercury ion or something weird like that too. we would want to look up the mechanism. If we're going to actually do this, we want to look up the mechanism with more detail to see exactly what that means. But it means you need both of them at least, either as a catalyst or a reactant. My guess is with this one that the zinc is going to be the reducing agent and the mercury is a catalyst, but you can't have, the reaction won't happen without both of them either way.
So you get like better yields than isolation.
Yes. So the alkylation, one, for two reasons. One is that the alkylation goes through a carbocation intermediate. You put the chloride, the alkyl chloride with the Lewis acid. It makes the carbocation to rearrange. So it's not as specific, especially if you want to wind up with a primary or what was a primary carbon attached. If you try to do this through alkylation, you wind up with an isopropyl group instead of an N-propyl group. So, and the yields are like, I want to say the acylation, the yields are in the 80s, and alkylation maybe in the 50s to 60s.
And I figured it must be something because like you gotta be really good.
Yeah, it's not a, and it's not a convenient reaction either. The zinc and the mercury, and you're adding a whole nother step. It's because that the alkylation is just not that effective. But the net result of that is that you were able to, after you acylate something, you're able to turn it into an alkyl group by just reducing it, and it's a full reduction. That one only works when it's in the benzylic position. If you have a benzylic carbonyl group, you can reduce it all the way to an alkyl group. You can't just take acetone and reduce it to propane. Doing that, you can take acetone and you can reduce it to propanol by using sodium borohydride. But the fact that it's in the benzylic position specifically is what allows this reaction to happen. All right, so then go back here for a minute. So we've got a series of reactions here. For A, what are the steps going to be? What is step one going to do? Close. So it is adding a nitro group. So remember, we go with whatever's the stronger activators in control. And so the methyl is a weak activator. The bromine is weak deactivator. So the methyl is in control. So it's going to be ortho to the methyl. And then the second two steps, just take the nitro group and reduce it to an NH2. So our final product here is going to look like that. So for the second one, it's going to be an acylation. We're going to attach the carbonyl benzene ring. Doesn't matter where we attach it. They're all identical, right? And then we're going to follow that up with the reduction that we were just talking about, that zinc with mercury I was thinking about what you're saying. They've got to be motivated to work with mercury. I mean, you frankly have more experience working in industrial chemistry than I do. But in academic settings, most chemists don't think twice about using hazardous materials. Maybe it's just because we have access to them whenever we want, they're not restricted in any way, or it's not our own pockets, we're paying for the disposal. But in general, most academic chemists would blink an eye at that. Mercury is not all that bad, frankly, it's probably easier to deal with than chromium for the most part. But yes, it's still, I also was educated before green chemistry was really a thing. It was widely spread, so that could have changed since I've been in a research lab.
All the stuff that we use comes out of the ground. But problem isn't that it's there, it's where it is.
Yeah, there's a big element of NIMBY. You know, we don't want to have to dig up parts of the country we like to get the mercury we want.
Or it's more like, you know, as long as the mercury stays like out of lakes and stuff.
Right, right.
It's all good.
Yes, exactly. And we have gotten a lot better at that. Yes, out of people too. It's like, no. And I don't know who I was talking to, but I think chemical recycling and sort of mining chemicals from waste facilities in the future is going to be a really big deal, because you've got this area where all of this chromium and mercury and other toxic heavy metals have been stored, you know, sequestered for the last 50 years. They've been accumulating there, and mercury prices start to go up because it's hard to get raw materials from China and Russia, and pretty much all raw materials come from one of those two countries. It might be more advantageous and economical to just go reprocess the waste facility and turn that back into usable mercury and chromium, rather than go dig up the earth. In Tokyo, all the Olympic medals were made from metal that was reclaimed from landfills. So they made all the gold medals and silver medals from electronics that were in landfills. You know, I think that sort of approach is going to become more and more common, because we have lots of good stuff in wastes. All right, so C, we're going to add a methyl group and then turn it into a benzoic acid group. So we just need to know where to put it. So it's going to go in the ortho or para position to the isopropyl group, probably favoring the para position given the sterics. So our most common product here . Look like that. And if we have an excess NBS, so remember NBS and bromosuccinimide, so a brominate benzylic position or an allylic position, but there has to be a hydrogen there to remove. So if it's a T-butyl group, we're not going to touch the T-butyl group, because it all doesn't have a hydrogen that the NBS can replace. If it was the isopropyl group from the example right above, and we had excess NBS, we wind up putting 3 bromines on the methyl group that we added, and then 1 on the isopropyl group, because it has 1 hydrogen that can be removed. But with it being a T-butyl group, our substitution is going to happen preferentially at the para position because of sterics. And then we put 3 bromines on that benzylic methyl group that we just added. Then if we did another substitution, and our choices are put it ortho to the T-butyl group or ortho to the tribromomethyl group. Now, so the tribromomethyl group is even bigger than a T-butyl group, right? So it just takes, part of it is just sort of developing that intuition of, I know a bromine is bigger than a methyl. So the only reason I'm pointing it out, I would not usually then, it'd be pretty uncommon to then take this and put it through another series of substitutions. But if you did, just to give you some context, that tribromomethyl group is a huge group in terms of sterics. Bromines individual, one bromine is almost as big as a T-butyl group. So to put 3 bromines there would be really, really big.
They're like,
Well, you'd have the two groups competing with each other as far as which one was more likely based on to be the ortho director.
I keep seeing that we're using like chlorine tanks for this, isolation stuff. Is that just favorable for economics? Similar would
Likely.
the same thing with like iodine. Would that like
So iodomethane is not going to form as favorable of a Lewis acid complex. You would need something else in that case. So that might actually be what the holdup is. Chloromethane is not pleasant to work with because it's a gas at room temperature. It's less than ideal. But aluminum trichloride is really common and really cheap. So versus iodomethane might be better to work with as a liquid. But if you have to use like a mercury iodine complex to get the same effect because of the size of the atoms, that overrides that. So it's a combination of things. Probably it's ease of use in the laboratory, economics, what's going to give better yields. It's possible that even though bromine is a better leaving group, that the chloride forms a better Lewis acid complex, and so maybe that has something to do with it, or might it just be rates? Aluminum trichloride is more soluble in your solvents than iron is, and so it would be one of those things that without knowing where you were headed and what kind of lab you were working in, it's tough to say exactly why it might be favored. Again, most of my organic chemistry knowledge, though extensive, it's on the theoretical side, not the synthesis side. So I'm the wrong chemist to ask about that. All right, that's the end of the chapter. So we finished up chapter 18 at this point. And again, there were a couple reactions we sort of glossed over because they involve oxidation in metals, and those mechanisms never, I shouldn't say never, but generally speaking, we gloss over those because that's a whole different realm of chemistry. We will get to some organometallic chemistry if we have time later on, but it really is its own class because of the way they behave. Although it does have some of the best named reactions. I've always been a fan of the Heck reaction. Richard Heck, Dick Heck.
What a name.
What a name. All right, so we'll go ahead and end early today. We have lab today. I'm going to run to the grocery store and get dry ice and make copies, and then Miranda, I'm probably going to upload that other copy once I get back. I want to get to I have a habit of once I go to my office and sit down.
It's hard to leave, I get it,
Yeah.
yes. No, that's fine.
So just remind me if in lab, ask if I've done it.